Okay, so we'll do this practical problem that will evaluate the performance of an ideal reheat cycle. So in this problem, we have that steam is the working fluid in an ideal Rankine cycle with superheat and reheat. Steam enters the first stage of turbine at 8 megapascal, 480 degrees, and expands to an intermediate pressure of 0.7 megapascal. It is then reheated to 440 degrees before entering the second stage turbine, where it can expand to the condenser pressure of 0.008 megapascal. So here, if you want, we are trying to compare with the previous problem. We considered the same extreme pressures. So P low and P high are the same. And we'll see how the reheating process will allow us to get better efficiency of our cycle, in addition to overcoming the limitations of a relatively low quality at the exit of the turbine. Now, the net power output of this system is 100 megawatt. We want to determine the thermal efficiency of the cycle, the mass flow rate of steam, and the rate of heat transfer from the condensing steam as it passes through the condenser in megawatt. And this will help us by comparison with the previous problem to discuss the efficiency of including this modification to our conventional Rankine cycle. So instead of dealing with one turbine, we are dealing with a multi-stage turbine, and will pass the steam through the boiler in two stages. So we'll have, if you want, two heat inputs. We have QN1 and QN2. Okay, but of course, this will affect also the overall performance. And it doesn't mean that if we are heating two times that it's not good, because we need to find the ratio. What we care for is the efficiency, W dot net over Q dot N. Okay, so let us do the analysis of the cycle. So as we mentioned, if we want to do first, if you want some analysis on the graph for the same quality at the exit of the turbine, okay? If you want to reach the same quality, in case we are using one stage turbine, we need to reach really a very large temperature at the exit of the boiler in the first stage. So of course, this will be very critical concerning the material. So here you can see that we need to increase the temperature to a high extent if you want to reach the same quality at the exit of the turbine. So in order to avoid thermal constraint for our turbine, we said no need to heat until this temperature. We can limit ourselves to a temperature below the maximum allowable temperature. And then instead of expanding in one step, because if we expand here in one step, we'll get a low quality, okay, at the exit of the turbine. So we'll expand in two steps. First, we expand to an intermediate pressure using the first stage turbine. Then we take the steam at the exit of the turbine and we pass it again through the steam generator in a way to heat it to a certain temperature, T3, before expanding it again in the second stage turbine. Of course, how we decide on the limiting temperatures, or how we decide to which amount we should heat, this depends, and we can do like a parametric study. So what is the temperature needed, for example, in order to reach the desired quality? Let's say we recommend, for example, a minimum quality of 90%, let's say. So we can say, in order to obtain this quality, what should be the exit temperature from the boiler? Okay, and in this way we can vary our parameters to study the effect of this temperature on the quality and on the performance and thermal efficiency of the system. So now, here they gave us all values needed. They already determined the conditions under which they are working. And all we have to do is to perform our calculation. Okay. So to start with, for point one, we have two properties. And keep in mind that whenever you have two properties, you can know the state that you are in. And in general, when they give you both pressure and temperatures, you are not inside the dome. Because if you have a phase change, pressure and temperature will cause no need to give the two, because once I know the pressure, I can determine the saturation temperature. Okay, so inside the dome, they give you or the pressure or the temperature with another value. So they can give you, for example, the entropy or the enthalpy, etc. Sometimes you just know the entropy, let's say, and the enthalpy, and you can get the conditions that you are in. So you need two properties, but inside the dome, they don't give you both P and T because they are related. But outside of the dome, they can give you P and T. So since they gave us P1 and T1, we are sure that we are not in change of phase. And since we are in the exit of the boiler, then we can consider that we are in the superheated region. Okay? So we can go to our superheated table and we can find for this point all properties needed. In general, we need the enthalpy, H1, and we need the entropy. We need entropy S1 because from 1 to 2 we have an isentropic process, so the entropy is constant. And we need to get S1 because S1 is equal to S2. So now for point 2, the two properties that we know are S2 and the pressure, which is P intermediate, because in the first stage turbine will expand to the intermediate pressure. Okay, so now for this point, once we know two properties, for this point we know S2 and P2. So since we know the pressure and we know that we are in a change of phase, we can know that we are in change of phase because if you go to the table of pressure entry for mixture, okay, you know that at saturated for mixture state, they give you SF and SG. And since S2 is between SF and SG at 0.7 megapascal, so we are within the dome. Okay, and therefore we can get the quality. We can calculate X by saying that X, the quality at this point, is equal to S2 minus SF, of course, at this pressure, at the intermediate pressure, over SG minus SF. And now once we get the quality X, we can find whatever we want. We can find the enthalpy and any other property of interest. So now we can say that this X is also equal to H2 minus HF over Hg minus HF. And this will allow us to find the enthalpy at this point. Okay? Now, we move to state 3. For state 3, what do we know? We know that we are heating in the boiler, and we know that in the boiler, we heat at constant pressure. So between 2 and 3, the pressure will remain equal to the intermediate pressure of 0.7 megapascal. So point 3 is characterized by the intermediate pressure and by a temperature of 440 degrees. So again, since they gave us pressure and temperature, we are sure that we went to the superheated region. And then from pressure and temperature, we can get the property of interest here, which are H3, the enthalpy that we need in the energy balances. And we need also S3, because in the second stage turbine, we have adiabatic expansion, isentropic expansion. So S3 is equal to S4. So now for point 4, it's similar to the analysis of point 2. We know that the pressure is equal to P low, and we know that the entropy S4 is equal to S3. So we have these two properties, and we can, from the table, know that S4 is between SF and SG at 0.008 megapascal. So we can find the quality at point 4, And from quality, we can deduce H4. So this is how we get the enthalpies of our points. Now moving to 5, as I told you, in general, if they don't say anything, always at the exit of the condenser, you take saturated liquid. And you need to determine at point 5, you will take S5 because you need it. You can take S5, but in general, for the pump, we don't use that S5 equal S6 because we are in compressed liquid zone, and sometimes we don't find these properties in tables. We can use another approximation that is knowing here, if you want, the specific volume at 0.5. We always say that for a liquid, we can treat it as incompressible. The specific volume will not vary between 5 and 6. So V5 is equal to V6. And you can use this to determine the work in your pump. W dot pump which is equal to V5 times delta P, which is P. In the pump, you will pump from the low pressure to the high pressure. Okay, so delta P will be P high minus P low. And if you do the energy balance for your pump, P high minus P low times V5 is equal to delta H. Okay, so it's equal to H6 minus H5. And H5, we can get it. H5 is saturated liquid, HF, which is enthalpy of saturated liquid at the pressure P low, at P low. Okay, so now from the energy balance of the pump, you can calculate your final enthalpy, which is H at 0.6. So always in a cycle, we need to determine first the enthalpies at different points because we need them in order to find all other properties. Okay, so to start with, for the thermal efficiency of the cycle, we should keep in mind that the formula in general is W dot net over Q dot N. Okay, but here W dot net is divided into several parts because you have two stages of turbines. So you should say for W dot net, I should account first for W dot turbine in stage 1 plus W dot turbine in stage 2 minus, of course, W dot pump. Okay. And for Q dot N, I should divide it into two parts because I am heating in two stages. First, from 0.6 to 1. From 6 to 1, I have the first heating process, and then from 2 to 3. Okay, so Q dot N per unit mass flow rate is equal to H1 minus H6 in the first heating stage, and plus in the second stage of heating, I am heating from 2 to 3, so plus H3 minus H2. Okay, this is for the heat rate per unit mass. Now for W dot per unit mass, so this is small w, okay? I have for W dot turbine 1, what do I have? We have H inlet minus H outlet from the energy balance. So it's H1 minus H2. For the heater, I consider out minus N because in the heater, I add energy. I add heat, okay? So H1 is larger than H6 and H3 is larger than H2. However, in the turbine, it's the opposite. In the turbine, I produce work, I lose energy. So W dot turbine 1 is H at inlet, which is H1, minus H at outlet of the first stage turbine, which is H2. This is for the first stage turbine. For the second stage, I have the inlet is at 0.3 and the outlet at 0.4. So it's H3 minus H4. While for W dot pump per unit mass flow rate, it's H6 minus H5. Okay. Now, so now I can calculate my thermal efficiency. My thermal efficiency, which is the ratio, okay? It's, as we said, I consider a W dot turbine 1 plus W dot turbine 2 minus W dot pump over, now I should add Q dot N per unit mass 1 plus Q dot N2. So as we said, it's H1 minus H6 plus H3 minus H2. And if you compare the efficiency here with the efficiency in the previous problem, you will see an increase in efficiency. And this was expected because because of the reheating process. Okay. Now, in the second question, they asked for the mass flow rate. We don't know what is the mass flow rate in our system, but we know that W dot net, they gave us W dot net, big W dot, and they give it in what? Okay, they give it in what? And since we know that W dot net is equal to the mass flow rate M dot times small W dot times small W per unit mass, yani W, this will be in, when I consider in joule per kilogram, I do delta H, okay? So M dot times a small W in joule per kilogram, turbine 1, plus small W turbine 2, minus a small W pump. All of these are in joule per kilogram, and to get them, I already got their expressions. WT1 is H1 minus H2. WT2 is H3 minus H4. Small W pump is H6 minus H5. When I multiply them by M dot, the unit will be in what? Because M dot is in kilogram per second. So kilogram will cancel out, and the unit will be joule per second, which is what? Okay. So I can say that small q is q dot over m dot, and small w is w dot over m dot. Okay, so now I need m dot. Because I need m dot, I already evaluated small w, which is W turbine 1 plus W turbine 2 minus W pump. And I have the net output given, the big W dot. So I can evaluate M dot as the ratio of the net output over the specific output in joule per kilogram. Okay, so all I have to do is to divide by W, small w, which is H1 minus H2 plus H3 minus H4 minus H6 minus H5. So then I can get the expression of my mass flow rate. Okay. Now, in order to determine the rate from the condenser, all I have to do is to take an energy balance for my condenser. At my condenser, I am rejecting heat. So at exit, H5 is smaller than H4. So if I write the energy balance, I will have that Q dot out, condenser, is equal to M dot, that I calculated now, times H4 minus H5. If they ask you, how can I improve the thermal efficiency of this system? You can say, I can do heat recovery and profit from Q dot out. So if I have a high efficient heat exchanger, let's say if I have a heat exchanger of efficiency 90%, so 90% of the heat rejected will be used to, for example, to heat a certain fluid. So I can say that if I calculate the new efficiency of my system, instead of just having W dot net over Q dot total Q dot N, what will be the new efficiency if I profit, let's say, from 90%? So if I tell you I put at my condenser a heat exchanger with efficiency of 90%, calculate the new efficiency of the new cycle. Okay, you can just say that now the efficiency can be calculated as W dot net, which is the power, the net power output, but I add to it, okay, I add to it 90% of Q dot out because I was able to profit from 90% of this heat that exit my condenser. And Q dot N didn't change, okay? So Q dot N total, I divided into two parts, Q dot N1 plus Q dot N2, okay? So heat recovery will always increase my efficiency because the denominator will remain the same, but the numerator will increase because I added this component to my useful, if you want, this is the useful power, and this is the useful heat, okay? And in this case, as we'll see in the coming slides, we say that we did cogeneration. What do we mean by cogeneration is that we used the same cycle to produce two different outputs. This can give me an electrical power, and this will give me heating. I can use it for underfloor heating. I can use it for domestic hot water needs, etc. Okay, so now the last question is to discuss the effect of reheat. So if we consider reheat, first, on the advantages level, I have first an increase in the quality at the exit of the turbine. I have a limitation of the maximum temperature reached in my cycle, and I have an enhanced efficiency. Okay, so all of these were reached by using this idea of reheating my steam in the boiler. So to see the effect of reheat, we can compare the present values with their counterparts in example 8.1. With superheat and reheat, the thermal efficiency is increased over that of cycle in the first example. And for a specified net power output, a larger thermal efficiency was reached, which means that I can circulate a smaller mass flow rate for the same output. Okay. Moreover, with a greater thermal efficiency, the rate of heat transfer to the cooling water is also less, resulting in a reduced demand for cooling water. With reheating, the steam quality at the turbine exhaust is largely increased over the value of the case without reheat. So all of these are advantages of reheat cycle compared to a cycle without reheat. Now, because reheating was really successful, okay, we did a lot of advancement in technology, in metallurgy, if you want, because we were able to come up with alloys that can sustain very, very large temperature. So we said that one of the limitations that we are not able to exceed a certain temperature. That's why we developed, if you want, new alloys that are called super alloys that can sustain really high temperatures, because higher the temperature here that we reach, we have seen that we can reach better efficiencies. And also we were able to overcome the dome in majority of our cases before, because of metallurgical limit. We didn't heat up to a very large extent, and we didn't exceed, if you want, the change of phase dome. But here, since we were able to have materials of very good properties, we can work with very high pressure and temperatures. And then you have, if you exceed this maximum limit here, you will not need a change of phase to go from one state to the other. So this is what we call supercritical cycle. So we go from liquid to vapor without phase change. Okay. And because we were able to come up with alloys that can sustain such pressures and temperatures, because of metallurgical advancement, we were able to enhance a lot the efficiency of such systems. So, as indicated in the figure, when we talk about supercritical cycle, in process 6.1, which is heating in boiler in a first stage, okay, steam generation occurs at a pressure above the critical pressure. So critical pressure, if you want, is a maximum pressure for which I have change of phase. If I exceed this pressure, I will overcome the dome. Okay, so no phase change will occur during this process, and we don't need a conventional boiler in this case. Supercritical cycles were constrained by metallurgical limitations, but nowadays, because of technological advancements, such plants can produce steam up to at pressure up to 30 megapascal and temperature up to 600 degrees, uh, which resulted in really high efficiencies. And if you compare efficiencies that we started with, for the first cycle, we got efficiency around 30%. And then by inducing reheat, we reached values up to 40%. And now by doing metallurgical advancement, we were able to reach efficiencies up to 47%. So whenever you increase the efficiency of your cycle, then you optimize energy use and you reduce, if you want, need to have backup systems or need to have non-conventional, more fossil fuels, because let's say the source is fossil fuels. For the same output, if you have higher efficiency, you need to burn a lower amount of fossil fuels. So this will save, if you want, money. This will save CO2 emissions and will save global warming effects resulting from these gases emitted by fossil fuel burning, etc. So enhancing the energy efficiency will help us on environmental level, on economical level. So it's very interesting to continue to research for advancement in technology that can lead to increase in efficiency. And ultra supercritical plants using newly available super alloys can produce steam at up to 35 megapascal with 700 degrees, with thermal efficiencies exceeding 50%. So as you can see, technological advancement were always helpful into having a more efficient use of energy. Now, we have a lot of strategies for improving performance, okay? And the majority of them are based, if you want, on or heat recovery or reheating, or including, let's say, a heat exchanger within the cycle. And one idea, which is called regenerative vapor power cycle, consists of including within the cycle a heat exchanger that will exchange heat between two streams of flows in a way to enhance the thermal efficiency. What is the idea? For example, here, instead of taking completely all the fluid expanding from the first stage turbine and taking it to the boiler, okay, which will add a certain Q dot N. The idea is that I don't want to add Q dot N, but I want to take a fraction of this fluid that can help me in the heating process, okay, from 5 to 6. Because if I heat using this stream, my fluid that is exiting pump 1 from 5 to 6, I can reduce, if you want, the total value of Q dot N. How? To understand this, we can look at the cycle. If you draw the conventional cycle, in the conventional cycle, you have this. You have 4 steps. Okay, I have one pump that will pump directly from point 4 to point A. So I will enter my boiler at point A. And in my boiler, I need to heat from A to 1. So I have to, Q dot N will be for this whole phase. So I have large Q dot N, okay? While if I introduce this modification, what will happen is the following, okay? So here first, I have two stages of turbines, and I have different mass flow rates circulating in my system. First, I have from 1 to 2, the circulating amount is the total mass flow rate, 1. So the fraction is 1. But now, after point 1, I divide my stream into two values, one going through the heat exchanger, which is called an open feed water heater. An open feed water heater is a heat exchanger that will mix my my flows, okay? Because it's mixing them, the heat exchange will take place under same pressure. So I have a certain pressure that is provided for me. I tell you that this open feed water heater is working at an intermediate pressure. I give you the value, okay? So you can know first that point 2 is at P intermediate. It's at the exit of the first turbine. So we can say that the pressure in this system should be at the pressure at exit of turbine of the first stage turbine. So the open feed water heater is operating at the intermediate pressure, okay? Now, this stream that is leaving the first stage turbine will be mixed with another flow that we'll discuss anyway, okay? So now let us follow the procedure. What will happen from 2 to 3? So here at 2, the fluid is divided into two parts, one going through the open feed water heater at a fraction Y, and one other part will go through the second stage turbine. So here I will have 1 minus Y, a fraction of 1 minus Y, okay? After this, the fraction 1 minus Y will expand in the second stage turbine to reach the low pressure, to reach the lowest pressure P low. And then in my condenser, still what is the fraction circulating here? 1 minus Y, okay? Until here I have 1 minus Y. So what will reach point 4 is the fraction 1 minus Y. And as usual, at exit of my condenser, I consider saturated liquid. But now, since this stream, okay, I want to profit from the high temperature of fluid at state 2 in order to heat my fluid before entering the boiler. Because when I heat it before entering the boiler, this will reduce the heat input of my cycle. So I expect that this will enhance the efficiency because I'm reducing Q dot N, okay? So what will happen here is that before entering the heat exchanger, I need to reach P intermediate because as we discussed, the open feed water heater will operate at same pressure, which is P intermediate. And since now at exit of my condenser, I have P low, I need to pump my fluid, I need to increase its pressure. So it will pass through a first stage pump. Why we need here two pumps? Because first we need to pump from low pressure to intermediate pressure using pump 1, okay? Now, once we reach the intermediate pressure, we are ready to mix the two fluids. So we mix the two fluids of fraction Y at temperature T2, which is relatively high, and fluid at state 5, which is at a lower temperature. But when we mix them, we'll be able to heat, if you want, fluid from exiting the pump from state 5 to state 6. Okay, so in general, in the open feed water heater, we can heat up to this saturated liquid point. Okay, so T6 is larger than T5 and smaller than T2. And now, once we mix them, we are ready to enter the second pump stage, okay, in order to pump us from P intermediate to P high in order to enter the boiler. But now, instead of entering the boiler at state A, okay, we enter the boiler at state 7. So now let us look together. Instead of heating from A to 1, we're just heating from 7 to 1. So this is the heating process now. I saved a lot of, all of this part is saved, okay? So I saved a high amount of input of heat by introducing this open feed water heater. It's true that I added an additional pump, but the pump power is really small. And if you want to calculate now your efficiency, your thermal efficiency here will be equal to, but just please pay attention now that the mass flow rate is not the same that is circulating over the whole cycle. That's why when you do the analysis per mass flow rate, okay, so when you take, if you want small W net over Q net, okay, first, for small W net, what do we have here? We need to consider first the value of W turbine 1. So I should ask myself, what is the fraction of mass in turbine 1? It's 1, okay? So I just consider that W net is equal to W turbine 1 multiplied by 1. So by 100%, since the fraction of flow rate is 100. While for W turbine 2, I just have a fraction. So the fraction is 1 minus Y. So plus W turbine 2. If you want just here to explain what I'm saying, W turbine 2, when you want to calculate it, you should consider 1 minus Y. So here times 1 is not for W, it's for delta H, okay? And here, what is W turbine 1? It's equal, okay, to 1 times H1 minus H2, okay? But when I consider WT2, because I have a fraction of the mass flow rate, okay? I have a fraction of the mass flow rate, so I can consider that I have 1 minus Y times the difference in enthalpy between points 2 and 3. So times H2 minus H3, okay? So pay attention to consider the mass fractions when you calculate WT1 and WT2. Now, what do I have here? I have 2 pumps. So I should subtract minus small w pump 1 and minus small w pump 2. Okay, and here also I should pay attention for the fraction. In pump 1, what is the circulating fraction? It's 1 minus Y, okay? While in pump 2 is after the open feed water heater where the 2 flows will mix together. When they mix together, I have Y fractions that will be added to 1 minus Y. So in the pump 2, I have the total fraction of my mass flow rate, which is 1. Okay, so now when I evaluate WP1, I should multiply by the fraction, small WP1. I do 1 minus Y times H exit minus H inlet, so H4 minus H3.